that this second regime does better than the first. What I just showed you was this particular regime right here. Start flat, go from flat to upright, go from splayed to upright, start upright, and end upright, okay? This was the one, the no scaffolding regime that I just showed you, where it starts the evolutionary run with vertically displaced legs and ends the run. This is what we refer to, not as the commonly known acronym for BS, but between scaffolding. So what we do here is the only body plan change is between lifetimes of the simulated robot. So it starts flat, but as any one robot is behaving over its lifetime, if you like, there's no change, okay? The rest of these are within scaffolding. So the body plan is changing over evolutionary time, and it's also changing over the lifetime of an individual. So thinking about how you get from prone to upright, I thought of 4 different trajectories you could think of. This one, it starts flat, goes to upright. Here it starts flat and goes to upright over the first 2/3 of its lifetime, and then spends the remainder of its lifetime upright, first third, and so on. So these are different kinds of changes in developmental trajectories, okay? You could probably imagine more of them. So we have 6 different experimental regimes. We did 100 independent evolutionary runs of each of those regimes. So here are our 6 evolutionary regimes down here. The vertical axis is the time in CPU hours to completion. So what we did in this set of experiments is we put the block 20 meters right in front of the robot, so it doesn't need to turn, it just needs to run forward. It takes all of the 6 regimes about an hour, 1.25 CPU hours to find a solution. So again, it doesn't matter whether we start with an upright robot or go from a prone robot to an upright robot. The embedded lines that you see here are the average time it took it to end the first phase. So all of these little bars down here, this is it evolving with the prone position. On average, after about, 10, 15 minutes, it discovers how to get to the block, and the prone position goes on to the next developmental trajectory, and so on. So it takes it a little while to figure out how to walk with its belly on the ground. It then rapidly transitions through these partial developmental trajectories until it comes to this 4th and final phase, which again is the same over all 6 regimes, is that the robot starts upright and ends upright. As you can see, it takes longer here, but actually shorter, takes less time than when you start the run like that. But there's no statistical significance between these. We then made the task harder, where we put the target object 20 meters away and 22.5 degrees to the robot's left. You can see all the bars have jumped up, so it's now a slightly more difficult task. The robot has to turn and locate the object, but still no statistical difference. We make the task more difficult again. Now we put the target object at 45 degrees off to the left, and now we start to see statistical significance. We've made this task even harder, and this difference starts to become even more pronounced, but I don't have those results with me today. So on average, if you start your evolutionary run with an upright robot and end, it takes about 3.5 hours, and these still take longer but much less time, even though you're passing through these 4 different phases. So these algorithms are more complex. They incorporate evolutionary dynamics and a very simple developmental dynamic, but they do better than leaving them out. Okay. Another thing that's interesting we found is that it's significant across all 4 of these changes in developmental trajectory. So you could argue that, well, we just happened to fix a good developmental trajectory and we spent a lot of time playing around with different kinds of developmental progressions. You'll have to take my word with it that we just basically came up with these in a brainstorming session. We tried all 4, and all 4 outperformed the control case. You'll notice that there is no statistical significance between the case where we have no scaffolding and only evolution. So only do we periodically change the body plan, but within the lifetime of the robot, there's no morphological change, and that doesn't do so well. So this argues that at least in these simplified experiments, you need to include both development and evolution. You can't just use an evolutionary algorithm. Okay, I'm running out of time. Rolf, any idea how much more time I have?
You have at least 5 minutes.
5 minutes, okay, that sounds about right. So why did evolution and development make things better? This is some preliminary results that I think argues for why these additional mechanisms helped. What I did is I went back, and in all of these regimes, at the end of each phase, I took the evolved controller that allowed the robot to successfully locomote towards the target